Hi, everyone. Welcome to our virtual informal systems seminar this week. We have our speaker, Fabio Coppini.
May briefly ask, I noticed that you record this talk. Is it possible to somehow download it or access later? Do you make it available?
Yes, we make the recording available afterwards.
Okay. Okay, that's great. That's good to know. Thank you.
Yeah, we recently implement uploading the videos on YouTube in the Gerard ISS channel, so that is available to everyone.
That's great. Great. Thank you.
Okay. So it's now it's my great pleasure to introduce our speaker, Fabio Coppini, today to the audience. Dr. Coppini has just received his PhD degree from University of Paris under the supervision of Professor Giambattista Giacomin. His thesis focused on linking classical results on interacting particle systems to new tools coming from graph theory, including graphon theory. And before, he obtained a master in pure mathematics in the University of Florence, Italy. So today, his talk will be on weakly interacting particles on dense graph sequences. So without further delay, let's welcome Dr. Coppini. Fabio, the floor is yours.
Thank you. So I hope that you can hear me and that you can see the slides.
Yeah.
So thank you very much for this invitation. It's a great pleasure to be virtually here with you and to be able to discuss the basically the main results that I obtained during my PhD thesis, which basically has just finished. So the seminar is informal, so please do not hesitate to ask questions whenever something is not clear. I will try to keep like the ideas as clear as possible, so I will not go too much into the details, but really to give you the feeling of, let's say, a journey in weakly interacting particles and graph sequences. So there are interacting particle systems are a huge so there is a huge part of mathematics talking about interacting particle systems, but I will focus on a rather precise class that will be clear in a while. So just to give you the outline of the presentation, I will start by giving you the general motivations and the background in order to state a question that will guide us through this presentation, to this seminar, and that will define the aim of this talk. And for answering this question,
Fabio, I think you're disconnected. Is it just me?
Yeah, I'm not hearing him either.
Not hearing him.
Okay.
I think he got disconnected. He's not in the list of participants.
Mm-hmm. Let's send him a message. Fabio.
Shuang, do you have another channel that you can use to communicate with Fabio?
Yeah, I'm sending him a message. I don't have his phone number yet.
But you have an email?
You
have an email connection, so you can use that.
Let's see. Sorry, just wait a few minutes before he could jump back.
of the presentation, I will, yes. So I said I will start with giving you the general motivations and the background, and basically stating a question that will guide us through this talk. And we will tackle this question about interacting particle systems and random graphs by basically analyzing two aspects. One aspect that is somehow related to pseudo-random graphs and mean-field limits, and another aspect which is probably more recent in current research, and which is about heterogeneous systems, so about graphon theory and an object that I will define at the end of this talk, which I call graphon particle system. Okay, so let's start by giving you the general motivation. So I go rather quickly maybe during this part. So the idea is somehow that we want to model complex systems in mathematics and like in physical mathematics, in applied mathematics, and we want to understand which are somehow the mathematical tools that are able to describe complex phenomena as synchronization phenomena. And you have many attempts coming from physics, biophysics, but also equilibrium statistical mechanics, like now dating 15, 20 years ago. But what will interest us, it's a more specific class of systems, which are called usually mean-field systems that I will describe you better in a slide, for which there are known results in the like, I would say, starting from the 20th century. And we will try to link these dynamical systems with the new insights coming from graph theory. And so in particular, I will study the complex network behavior by studying an underlying graph sequence. So a graph sequence which will be defined and underlying on these particle systems. And I will go from dense graphs to sparse graphs, saying something about the sparse regime if we have time, but mainly focusing on the dense graph and convincing you that this is already something interesting to do. So to give you the prototype model, we fix n, which is supposed to be large and which is basically the number of particles, and we fix a capital T, which is the finite time horizon on which we study our system. And we basically want to describe an interacting particle systems by a system of coupled the stochastic differential equations. So the idea is that each particle position is defined by a function, which I call xin for the particle I, and at time t, the dynamics is given by this system. So I'm giving you things here on R, so one-dimensional particles, but it is straightforward to generalize most of the results that I'm telling you to RD, so to any finite dimension. So as you can see, the dynamics on one particle is basically somehow there is a symmetry. So every particle solves the same dynamics, where you have a transport term given by F, and you have an interaction term given by gamma, and then you have a noise term given by sigma. And the initial conditions are denoted by xi, and I will say more on that later on. So the idea is that we assume F, gamma, and sigma to be regular enough. So we want to have a global solution. And so there are a lot of different results changing the hypothesis on F, gamma, and sigma, but we really don't care about this aspect during this presentation. So you can suppose that they are bounded and, like, for example, C2. BI are IID Brownian motions, but if you don't like stochastic things, you can also take sigma equals to 0. And most of the things that I'm going to say are basically true for deterministic systems. So whenever there is no randomness in the dynamics, you can obviously take the initial conditions to be random. What is interesting about these systems is obviously not really the dynamics of a single particle. It is not possible to solve, to have an exact solution of this system. So what we are interested into is the behavior of the population. So when we say population, we basically say empirical measure. So this is like the standard way of defining the empirical measure of a system. We are taking delta Dirac centered in the position of each particle, and looking at the empirical measure, it basically tells us how the particles are distributed over R in this case. So there is a slight abuse of notation because I'm saying that the empirical measure, it is a probability on R. it is obviously not a probability. It is not really into R whenever the initial conditions are random or whenever there is the Brownian motions are there. But so it is a random variable with values. But I hope that I can make this small abuse of notation. Okay, so about this system, there are a lot of results. And so they've been firstly studied. I think that the first result was by physicist Jean in the like 1904, something like this, and then Vlasov in 1914, and then we need to wait like the 50s and the 60s with the McKean, and then Snitman in the 90s. And basically the idea is to study the limit for n which tends to infinity of the empirical measure. And you can state a law of large numbers, you can state central limit theorems, you can state large deviations. And the flavor of these results is basically the following one. So you suppose that at time zero, the empirical measure is converging to some mu zero. So you suppose that you have convergence at the very first time, and then you can show that you have convergence at the level of the process. So mu n is not just converging at time zero, but it is converging for every time, for every t between 0 and t, where t is fixed. And the cool thing about this system is the fact that you can actually explicit the limit. So there's not just a limit, but you can describe, you can write it down, and this limit is the solution of a PDE, which is usually called Vlasov equation in the deterministic case where there are no Brownian motions, and it is called McKean-Vlasov equation when you add dissipativity, so when there is a Laplacian coming in from the stochasticity, from the noise term. And the key point is the fact that the interaction, which is written there, it is a function, it is an explicit function of the empirical measure. In particular, it is a linear function of the empirical measure. And so it has good properties with respect to, so it has continuous properties with respect to the measure mu. And by using this continuity, you can actually, so the result is really a result of continuity of the equation, right? You have convergence at time zero, you have continuity of the coefficients, and so you basically get the coefficients for all times. And if on the one hand, this is great for a mathematician because he's happy because you have something like, it has a nice limit at the end. I mean, nice depends on points of view, but it has a limit and you can write that down. On the other hand, you can see that the interaction is basically trivial in the sense that every particle is connected to all the others. So it is like the mean field hypothesis, which is basically stating the fact that I'm connecting everyone to everyone else in exactly the same way. It's like poor with regards to application. So we want to consider more general interactions. And one way to do that is to multiply the interaction gamma by 0-1 variables. So you're basically saying that when particle J is acting on particle I, then I multiply it by 1, and otherwise I multiply it by 0. And when you take all these 0-1 variables, then you put them together and you see that you have an adjacency matrix, which is basically a symmetric 0-1 matrix whenever the interactions are mutual. So whenever I is connected to J and then J is connected to I, and it is asymmetric whenever the interaction is not necessarily mutual. And as n grows, so you basically are defining a graph sequence where two particles are interacting with each other whenever the link is present in the underlying graph. And the prototype model becomes something like this. So there's the Xij variable, which can be random or deterministic. You will see different examples along this seminar. And then you have, so with respect to the previous expression, I added a term which is Pn. So basically, I want to compare this equation. I want to compare this system with the mean field system, with something that I know, right? So I basically want to assure that whenever I don't have a lot of connections, this term is of order 1. And let's say that I'm taking half of the connections, like with probability 1/2. So I will have basically half of the connection. So if I want to compare this system with the mean field system, I need to multiply the interaction by 2, so that they really just not have the same order, but somehow not just the leading order is the same, but So it's the same also with the constant, with the right constant in front of it. Okay, so one could try to replicate the previous proof, and then you see that the empirical measure, so now the interaction term is no longer an explicit function of the empirical measure, and you basically lose the continuity property of the equation, and you no longer know how to deal with that. So the interest of our talk is to understand the behavior of μn with respect to this coupled sequence of graph and Pn. So Pn, if you think a little bit more, nPn basically represents the average degree. So since I'm multiplying particle I and the interaction is basically the interaction with all the neighbors, the idea is that I'm dividing by the number of neighbors. So nPn represents somehow the number of neighbors. So Pn is linked to Xn being the average density degree per site. But this is not necessary. I mean, it will be clear later on. So what's the main question, right? This is a like general topic, understanding a system depending on a parameter, and can we be more explicit? And the answer is, of course, yes. And the very first question is, which are the graph sequences which yield the mean field limit? So we want to understand, we want to classify basically all the graph sequences for which when n tends to infinity, I get the mean field limit. And this is like a very simple question, because we expect that if we remove some connections like randomly, the behavior should be the same, and we should get the mean field limit. But for example, how many connections can we remove in order to get the mean field limit? So there is also the related question about the average degree. So how nPn, how the average degree should behave to get the mean field limit. And then you have like more difficult question, like what is the long time behavior of this system? And in this talk, I'm going to focus on the very first question. And basically, I will show you that this very simple question, which has been basically the guiding question of a big part of during my PhD, it is a highly overrated, I mean, underestimated, sorry. It is highly underestimated, because in order to understand the mean field limit, so in order to understand the graph sequences that converge, that make the system converge to the mean field limit, you also need to understand the graph sequences which lead to a different limit. And this different limit, I will call it graph and particle system, and it will be the last part, the third part of this talk. So just we are still in the introduction. Let me just give you that a first answer to this question. So to the very first question was already given, like in 2016, but also in another result by Badimi, Budirai, and Wu, basically at the same time. And the result sounds like this. So suppose you have IID initial conditions, and then you suppose that the graph sequence and the parameter Pn satisfy some condition that I'm going to describe, to focus on a little bit later. Then you have the convergence of the empirical measure in probability to the mean field limit. And looking at the proof is very simple, in the sense that you take your dynamics, you have a graph, so you add and remove the mean field dynamics, and what you get, so you have the mean field dynamics plus perturbation term given by the graph structure. And by using the independence of the initial conditions and this deterministic hypothesis on the graph, you can show that the perturbation given by the graph is converging to zero, because like you have independence, it is the mean is zero, and like sum of independent random variable with mean zero, it goes to zero as n tends to infinity. That's the proof in 2 minutes. And so now let's look at the deterministic condition on the graph. And so it is a supremum over I, so it is a uniform condition on the particles, and it says that when I look at the connections of every particle, so the sum of Cij, then it has to scale as nPn. And this is for all the particle, and the condition nPn goes to infinity is basically telling you that every particle's degree needs to diverge as n tends to infinity. So you basically just need the graph to be uniform with respect to the degrees to get the mean field limit. And so you have a lot of graphs, right, that satisfy this equation. And for example, you have Erdős-Renyi random graphs that satisfy this equation almost surely as long as NPN is diverging faster than logarithm of n. But also, if you think a little bit more, you have disconnected graphs that satisfy this hypothesis. Because obviously, you take two connected components, you put them together, a particle will have n over 2 or n plus 1 over 2 connections for every n. So in the limit for n which tends to infinity, every particle will have 1 over half density. And so the density will be all the same, but you have a disconnected graph. And so the previous result is telling you that a system on a connected component is behaves like a system on a disconnected component. So like this is like weird. But the point is the fact that you're giving a result in probability and you have taken IID initial conditions. So in reality, the law of the system on the two connected component is the same, and it is the same of the mean field limit. So basically, the takeaway message of this theorem is the fact that if you assume IID initial conditions, then you basically lose a lot of information on the graph. So you, at least on the finite time scales, you cannot say if the graph is connected or not. So if you cannot say if the system that you're looking at is connected or not. You can just say that the particles are has the same degree somehow. So the very first part of my work, of my research, was like trying to generalize the previous result and trying to state the result without asking IID initial conditions, so without asking any independence in the initial conditions, and really by trying to exploit the averaging properties of the graph sequence behind. And this leads me to the pseudo-random graphs, and basically, so pseudo-random graphs is a general class of graphs that was characterized in the late 80s, and that will come back again at the end of this talk. And one example of pseudo-random graph is given by Erdős-Renyi random graphs whenever the connections are enough somehow. So suppose that you take a graph and you build it this way. So you take Cij to be a Bernoulli random variable with parameter Pn. So you're basically saying that the link between two particles is given by probability Pn. So you toss a coin, and if you had, then you put 1, and so the two particles are connected. And you do this independently with respect to all the others. So you basically have Cn, so the adjacency matrix is a collection of n square or n square divided by 2 if you have symmetric matrix of IID random variables. And then you can prove that you just suppose that the empirical measure is converging, so you can take basically every initial condition that you want, but still independent of the graph sequence, and you have the mean field limit for almost every realization as long as the degrees are diverging fast enough. So basically the same condition that was in the previous theorem, NPN, which is diverging faster than log n. So now you look at the proof, and the proof on one hand is completely different from the previous one because no longer supposing IID initial conditions, it makes you basically, you cannot use propagation of chaos results and propagation of chaos tools that are like very useful in some cases. But that, on the other hand, it is very similar. So the idea behind is the fact that you still decouple the dynamics. So you still add this mean field term and you subtract it, and so you get mean field dynamics plus perturbation term. And now this perturbation term is again going to 0, not because the initial conditions are IID, but because the edges are IID, right? So you're basically exploiting another randomness, and you're mixing things now not by using the initial conditions. So now not by using the chaoticity of the system at time 0, but you're really using the chaoticity of the graph, of the underlying graph. Okay, so we have an example, right? And this example basically, so let me take it back. So it is telling me a few things. Okay, one thing is the fact that as long as we renormalize the dynamics, so as long as basically we divide by NPN, the result is not depending on the class of system. So it's like what it seems to matter is the structure of the graph and not really the number of vertices of edges. And this will be, I will touch this aspect a little bit more later on. So this is one key point, and the other is like, okay, we have actually a class, so we really don't need all the connections, and we can actually we can actually lower the number of connections to something like n log n, but we need somehow some homogeneous properties. So this is related to the pseudo-random graph notion. And then with Francesca Nardi and Gianmarco Bett from University of Florence, so they came to me once and they said, okay, Fabio, we would like to extend your results and like try to do this for other class of graphs. Like we can maybe slightly change Erdős-Renyi random graphs and try to see that even if we slightly change these graphs, you can actually still get the mean field limit, which is somehow reminding of statistical mechanics arguments where you basically get the mean field limit every time, like on the Ising models. Like I'm thinking about locally tree-like graphs and these kind of stuff. But the point is that if you try, and I tried, you try to change the proof and to basically change the construction of the graph, then you basically losing the fact that the particles, either that they are independent or the fact that they are identically distributed, you cannot proceed, and there is no way out. So this is somehow a poor result with regards to our application, because we cannot say something that is interesting for like scale-free networks, or for like real life systems where the connections are far away from being Erdős-Renyi. So this leads me to another chapter, to like heterogeneous systems. So let's try to add heterogeneity, like inhomogeneity to the system, and like try to see if there is a limit. And basically, during the same time that I was working on the previous result with Helge Dieter and Giambattista Giacomin, a few authors basically started working on graphons and on inhomogeneous random graphs, and they could give a limit which is different from the mean field limit for these random graph sequences. Like, to be precise, you have I think that the first one was Medvedev, who was studying while he was studying like the Kuramoto model, deterministic version, but also then there's Eric Lusson, Roberto Oliveira with his former PhD student Guillermo Reis, and later on Bayraktar, Chakraborty, and Wu. So they consider this more general class of graph that I'm going to define in a while, and they, as I said, they give you a limit which is at least formally different from the limit that we have seen. So before giving you the result, let me restrict the analysis to oscillators and like to a simpler dynamic somehow. But this is more a matter of not writing too many things on the slide, and most of the things again that I'm going to say holds for general particle systems on RD, where there is also a transport term and where there is also a diffusion coefficient which is not equals to 1. So now I'm considering like oscillators, so particles on the one-dimensional torus, and I'm still denoting the empirical measure by mu n. And another thing, I'm not dividing by Pn, so I'm restricting the focus to dense graph sequences, and I hope that I've convinced you that it is the structure that is really important and not really the number of connections. So whenever you take Erdős-Renyi random graphs, the mean field limit will have this p. So we fix p between 0 and 1. So the graph is basically dense with the number of connection, which is something like n squares times p. And you will see this p appear in the convolution with respect to mu. So this is like the Mekin-Vlasov equation related to the systems of oscillators that is written just above. And so you can see that the interaction is basically translated, translated into a convolution, and that the limit somehow of the graph is given in the case of Erdős-Rényi random graph by P. Okay, so now we can build a an inhomogeneous random graph, and the idea is the fact that we fix a function which is like reminding of the structure, which should give you the structure of the graph. And so it is a symmetric and measurable function from the unit square to the unit interval. We fix a sequence of IID uniform random variable on 0, 1, and then we define conditionally on UI the variable Cij to be independent Bernoulli random variable with the parameter which is now given by the function W computed on UI and UJ. So don't be afraid. So it seems like to be a strange construction, but it is actually quite natural. And so just take W to be equals to P, constantly equals to P, and then you get the Erdős-Rényi random graphs because Cij are now IID random variable parameter P. Then conditionally on UI, you can see that Cij are independent. So this is like a nice feature that we want to use, but they are not identically distributed. And on the reverse side, if you do not condition on UI, but if you see them as a random variable on its own, then they are no longer independent, but they are identically distributed. And so you can basically trick friends by once supposing that you are conditioning and the other time without conditioning, and you can get different results based on these two, but I'm not going into these details. So let's just stick to the conditionally on UI, they are independent. And then the last thing that I want to be clear is the fact that for every n, you get a dense random graph. So the number of connection is scaling as n square. And just to have an idea, if you look at the picture on the right, so this is like usually called pixel picture of the random graph. So this is like W, and the color is the value between 0 and 1. And here you basically have two connected components. So one smaller connected component, which is related to the particles. So to the particle I, for which UI is between like 0 and 1/3. So mostly to 1/3 of the particles will stay in a small connected components where you have a lot of connections. So this smaller connected component, it is like an Erdős-Rényi random graph with some P close to 1. And then you have another connected component, which looks like a scale-free network, right? Because you have particles, the ones with label, so for which UI is close to 1, who has a lot of connections, and other particles we have lower connections. So the idea of putting this W is basically that you want to encode the connection profile of every particle by just computing W in UI. Okay, so the first step in order to get this new inhomogeneous limit, inhomogeneous particle systems, is to observe that the randomness with respect to the Bernoulli random variable is not really playing a role. So since in the interaction you have a sum of basically independent things, at least you can see this, and the sum of independent things, you get that this sum, it is converging to the expected value of the sum. So you can prove that with high probability, the previous system is close to this system where you have replaced Cij by their expected values, conditioning on UI, UJ. And this is basically a matter of concentration inequalities technique. But then you look at the system, you see, okay, but this is instead of looking at a system on the torus times n to the power of n, I'm looking at the systems which is defined on the torus times the unit interval. So basically I'm looking at the dynamics of theta and u, where there is no dynamics on u, but where theta and u are coupled. So this is like a two-dimensional system defined on the torus times 0, 1. And so I can basically replicate the known results that I have for particle systems. So like things that are dating back to the 60s, 70s, maybe 90s, depending on the conditions, on the hypothesis of the coefficient. But the point is that now the double empirical measure, so with respect to the position of the particle and with respect to the label, you can prove under some regularity condition on W that is converging to the related PDE. And this related PDE is basically given by the following one, which has theta and x. And then if you want to get the empirical measure, like with respect to the position of the particles, you just need to integrate with respect to the labels. So you just need to integrate between 0 and 1, and then you get what I'm writing here as WPDE. And as you can see now, the interaction gamma is multiplied by W, which is basically weighting the interaction, and between particle X and particle Y, the interaction is no longer given by P, which was the case of Erdős-Rendi random graph, but is given by W. Okay, so let me write it again. And the point is that if you look at these results, that they prove that there exists a unique solution for this WPDE, no matter the regularity on W. So recall that for proving the convergence, they need W to be at least continuous. But then if you look at when you look at the proofs for like the existence and uniqueness of a solution, you don't need the continuity of W. So it exists, the solution exists no matter. So you just need to be symmetry and measurability for W. So you just need it to be a labeled graphon, so an element of calligraphic W0. And then this was proven by Gianmarco, Francesca, and me. If you relabel the particles, so if you basically do a measure preserving map on W, you get the same limit. So this is obviously like trivial. I mean, you have a bunch of particles, you relabel them, and then the empirical measure is invariant under relabeling, and so you basically get the same limit. But using this like simple fact, then you can prove that when you change W and V, so when you change the labeled graphon behind, if you change it in a way that so with respect to a specific distance, then you get like you can control the differences between the two solutions. So you're basically saying that the previous equation is continuous. And the point is the fact that these pseudo distance on the space of graphons, on the space of labeled graphons, it is actually the distance that characterizes the space of unlabeled graphons, which is the proper space of graphons. So in this result that was that we published last year, we can basically prove that the map that is mapping you an unlabeled graphon, which has no notion of regularity, because you are taking it is a class of labeled graphons with respect to measure preserving maps, then this map is continuous, and the topology that you are taking on the space of probability measure, it is like Wasserstein distance, so it is a very classical distance. Now recall what I told you at the very beginning by telling you about the known techniques for showing the mean field limit. So the idea is the fact that the equation is continuous with respect to the parameter. So when the initial condition is convergent, then you get the convergence at the level of the process. And so we came to this point to say, okay, but so it is the limiting PDE is continuous with respect to W as well. And the continuity, so the space of graphons, it is actually the space where you can study convergence of dense graph sequences. So it is a way to characterize the limit of dense graph sequences. So we should prove, it should be possible to prove that whenever a graph sequence is converging to an unlabeled graphon, then we should get the convergence of the empirical measure. And this is basically our main result. Let me stress two things. So one thing is the fact that we are supposing IID initial conditions, and I will be back to this point in a few seconds. And the second point is the fact that you can actually have more than that. So you do not need to consider W, so the limit in W, to be a deterministic graph on, but you can take it to be like also random. So you also have convergence for very, very general graph sequences as exchangeable graphs. So this limit in the end, which is different, at least on a first sight from the mean field limit, let me call it graph on particle system. So you have basically a collection of particles which is indexed by 0, 1, and the low of particle with label X, so the low of the particle associated to the profile of connections given by W computed in X, is given by this system, by this equation, which is so a coupled system of Fokker-Planck equations. And then you recall the mean field limit, and you can say, oh, but these two things are equal whenever W is constantly equal to P, right? So if you recall the first question that I posed, it seems we have an answer, right? So we can prove that all the graph sequences that are converging to constant graph on, which, by the way, are called pseudo-random graph sequences, lead to the mean field limit. And this is of course true. So every time you take a sequence, you just need to look at its limit in the graphon space, and it will have a limit because the graphon space, it is a compact metric space. So at least by taking a subsequence, you will get something there, and you will get a limit for the system. So it seems that that we have an answer. But the point is the fact that this does not mean that if you take some W which is strange, it will not give you a behavior close to the mean field limit. We only prove that whenever W and V are closed, then you get that the two solutions are close. But this, you can also have a W different from V, and then you don't know if the two solutions are far away. So we only get the right-hand side of the inequality of the inequality. And then the second warning is that remember that we are taking IID initial conditions, so there's something strange that can happen, and the fact is the idea is the fact that you take a graphon which has a constant degree. So for instance, you can take the Cayley graphon, and for the Cayley graphon, you basically have that every particle is connected to the same number of particles, to the same portion of particles, but this portion is changing every time. It's like a circle where you are connecting to your neighbors, to a non-trivial fraction of neighbors. And for this graph, you can prove that almost surely, as n tends to infinity, the degree are scaling as npn. So you basically get that the hypothesis of the very first theorem that I showed you are satisfied. So the empirical measure is converging to the mean field limit. But at the same time, the hypothesis of the last theorem that I show you are satisfied. So the empirical measure is converging to the graph on particle system. So this basically, it is an indirect proof of the fact that on this graph, mean field limit is equals to the graph on particle system. And you can see that a Cayley graphon is rather different from a mean field limit, from a constant graphon, or for a graph which you connect with components. And this is like a work that I've done recently, and so like it requires a little bit of work. So I'm stating here a corollary, and maybe if you give me 2 minutes, something more. So the idea is that if you fix the initial condition, and if the initial condition is not depending on X, so if you are basically not coupling the initial condition with the graphon, then you just need the degree of the graphon to be constant to get the mean field limit. And so the takeaway message that I want to leave you with is the fact that when you analyze such a systems, and especially if you have like interested in applications, you really need to be careful with the condition on the initial conditions. And the idea is the fact that if you want to study the graphon particle system, which has been introduced more like a formal limit, like we have the limit and we are happy, but if you study it a little bit more, then you see that it's not that simple. So you need to consider it not as a function of the graphon, just simply a function of the graphon, but a function of the coupled graphon and the initial condition. And okay, so let me give you another idea. So you can generalize the previous result by saying, okay, let's say that we have two populations, so that we partition 0, 1 with I and J, and we have the same initial conditions on I, and we have the same initial conditions on J. Then if the graphon, so if the subgraphons Wi in the I times I in the I times J, so in the 4 block have the same degree. So if basically the particles between the two populations are looking at the same proportion in the other blocks, then you have the final limit is basically a function which is constant on I and J. So the previous infinite-dimensional coupled system, it is actually reduced to a 2-dimensional system, so where you have two PDEs which are coupled together, and where this coupling is made basically by dA of x, x depending if it is on I and J. So that's the end. I hope that was clear, and I thank you very much for the attention.